So in this video, I want to discuss using the sense inputs on a power supply. The sense inputs basically allow you to control where the system senses the output voltage. In the last 2 or 3 videos, we've looked at this PMC power supply. I've got the picture of it up here that I picked up at the Mike and Key Hamfest recently. And there was a couple of things that caught my eye on this meter, or this power supply, and that's why I eventually picked it up. First off, it's 0 to 20 volts, up to 1.2 amps. That's a nice little range. This gets comfortably into 15 volts for op amps and that kind of stuff. And it's a good current range. 1.2 amps at 20 volts is a nice little supply. So that kind of caught my eye. The second thing is there's a current limiting control on it. So there's a potentiometer here behind this knob that lets you adjust the current point, where once the power supply hits that amount of current, it won't supply any more voltage. It'll maintain that constant current. So in this case, you could use this as a constant current supply, meaning I could put 5 volts across the load, bring the current up to say 200 milliamps, and then as I brought that voltage up, the current would stay the same. I can control the maximum current the power supply can generate. The next thing I noticed on the voltage adjust is there's two potentiometers here. There's an outer potentiometer and an inner potentiometer. The outer one is gross voltage adjust. The inner one is fine voltage adjust, and that's really kind of nice because it kind of speaks to this as a well-regulated supply. When I turned these knobs, when I picked it up, I could feel there was wire-wound potentiometers behind them rather than just a carbon film. And that wire-wound feel kind of said to me, again, this might be a little higher quality power supply. It uses, of course, standard banana jack outputs on the supply. There's the chassis ground here that goes back to earth ground. And both these outputs are floating. I didn't know that until I opened it up, but I assumed that. And with these floating, it means I can couple it to other power supplies and actually generate negative voltages if I need to. Get a nice little feature. When I turned the power supply around and looked at the back, this is what really caught my eye, is there's these screw terminals across the back. And of course there's your negative out and your positive out for your load, but there's also a negative and positive sense input. And what these inputs allow you to do is sense the voltage someplace further down in the load to make sure you have the correct voltage there rather than the correct voltage here. And we'll talk about this in just a second in more detail. If we go on to the next photo, I've actually removed the little jumper links. Let me go back and point those out. There's a jumper link here that hooks the minus out to the sense in and the positive out to the sense in. By removing those jumper links, I end up with these terminals disconnected on both sides. And this allows me to wire this in a mode where I can sense voltage where I want to, and it'll do what it needs to do here to produce that voltage further down circuit. So we'll talk about this a little bit more here. So in this case, I've got the sense jumpers in, and that means that the power supply is looking at these screw terminals to say, what's the voltage here? Maintain the voltage here. At higher currents, you begin to get voltage drop across wires and connections and those kind of things. So I may be telling the supply to output 5 volts, and it's maintaining 5 volts here, but there might be a tenth of a volt drop in the wiring, and I'm only getting 4.9 volts across the load. In that case, I wanted 5, but I'm incurring loss in the wires. That loss in the wiring, that voltage loss, will change with current. Think of the wire as a small resistor. As the current goes up, the voltage drop across it increases. So if I wanted a very accurate 5 volts here, and the demand of the load was changing, drawing in more current and less current, I want that voltage to stay 5 volts at the load. And essentially the resistance of the connections to not be in circuit. Another quick comment here is these 2 output tabs here are connected to the 2 terminals on the front of the meter. So whether I'm connecting here or connecting here, I'm connecting to the same points inside of the meter. So in this case, this is just set up with the sensing happening on the back panel of the device. If we move to actually using the sense jumpers, we'd connect like I've drawn here. So notice the jumper bars have been removed. I've got my power out to my load under test and back. So I've completed that circuit on the output of the power supply. And the current to the load is going to pass through the red and black wires here. And as that current load increases or decreases, the resistance of these wires, of interconnects and things in the way can make a difference, like I said before, and cause you to have a lower voltage at the load. By taking the sense inputs down as close to the load as I can get them, we can compensate for this. There's almost no current flow in this sense loop. It's just simply a voltmeter. And so if we're outputting 5 volts here, and we've got a 1/10 of a volt drop in the wiring, and running up with 4.9 volts here, the sense inputs will allow the power supply to say, hey, it's only 4.9, and he wanted 5. So drive the output up. And in this example, it would drive the output to 5.1 volts. We've got the, a 0.05 volt drop in this wire, say, and a 0.05 volt drop in this wire, but we end up with 5 volts exactly at the 2 connection points down here. Your current path is, the black and red wires where the actual current to power the load is happening. And again, the orange and brown are just simply, essentially a voltmeter. So we're going to do an experiment based on this on the bench. And what we're going to do is we're going to hook up my electronic load as it's shown here, so we can get it in a constant current load mode. We're going to add a 0.47 ohm resistor in a series here with the load, and what that'll basically simulate is voltage drop in the wiring, voltage drop in any connectors there may be, those kind of things. And with the sense down here, what we'll be able to demonstrate is with very low load in the circuit, the resistance is very high, and we're asking for 5 volts, we'll see 5 volts, down here, is that as we increase the current by reducing the resistance of the load, we'll start to incur voltage drop. And in this case, we'll be able to measure that voltage drop. Now, this is kind of a convoluted little configuration here. You wouldn't expect to have 0.5 ohm resistance necessarily in the wiring between your power supply and node. But if these wires were 3 feet long, and there's 6 feet of wiring, 3 feet to the load and 3 feet return, you could see a fairly high resistance depending on the gauge of the wire, those kind of things. So this isn't that crazy a configuration, but I'm going to use a resistor here so we can actually measure the voltage across the resistor. And from that, we'll be able to demonstrate as I drive more current through the load, that voltage will increase, and we'll end up with less effective voltage at the load if we weren't using the sense, because we have the sense leads connected. As we incur more voltage drop across the resistor, the power supply will drive the voltage higher to maintain a constant voltage here and do exactly what it's meant to do. The sense will sense the voltage where I want it to be and do its best to maintain the voltage at these 2 points, irregardless of any voltage drop across this resistor we'll have in circuit. It was really seeing the sense inputs on the back of this little power supply that caught my eye, and I said, for the $5 or $10 I paid for it, looks like a pretty decent little power supply. I'll pick it up, and we went through some repair work on it in some previous videos. It's got nice wire wound potentiometers for the voltage control. The design seems okay. There's a lot of heat sinking. It's a 20-plus-year-old design, it looks like. But it just seems like a really nice little general-purpose bench supply. So I'll get configured on the bench, and we will sit down together there, and we'll take a look at this. So we're set up on the bench here to try to kind of demonstrate the effect the sense inputs on the power supply have. So I've got the bench lights off here to try to reduce the glare on the 3 voltmeters down here. We've got a little schematic here kind of drawn up of what we've done. The meter here labeled V1 is measuring the actual drive output voltage of the power supply. So let's see if we can bring that back down to 20 volts exactly. Even with the gang pots, it's a little touchy. So keep tweaking up here. V2 here in the middle is measuring the voltage drop across that resistor. Remember, this resistor is kind of simulating the loss in the power lead. So the higher the current, the more the loss there is in the wiring and the connections. And because there's resistance in the wiring and connections, we get voltage drop there, and the voltage at the actual load, V3, can be less than what we're trying to provide. And so what we're demonstrating here is we have the output of the power supply set to 20 volts. We're measuring the voltage at the load. So V3 down here is measuring 20 volts. And I've got the electronic load off, so there's very tiny little current draw in the system. And these meters aren't perfectly calibrated to each other. So this V2 represents the voltage across this resistor here. Again, that resistor is kind of the emulation of VIN lead resistance and stuff. And what should happen here is as I bring the current up here on the load, we should see the voltage at the load, this here, stay steady, stay at 20 volts. And that's because the power supply through these two sense leads is measuring the voltage all the way out here at the load and keeping that constantly at 20 volts. And to do that, it'll raise the output voltage. So what we should see is the voltage here on V1 raise as the current demands go up. The voltage across the load stays steady, and the voltage on V1, the output voltage, should be the total of the voltage drop across that resistor plus the 20 volts at the supply. So what you should really see here is this guy should stay at 20. And the voltage here should increase, and the voltage here should increase together. So let's start to bring the load up. And I'll see if I can kind of approximate here. It's hard to read the meter. So we're getting up in the range of, will actually give me some current draw. There we go. So what we can see now is I still got the 20 volts at the load, but the power supply is outputting 20.1 volts. And again, 20 plus 0.11 is very close to 20.1 volts. And so what the power supply is doing is increasing its voltage drive a small amount to make up for the drop that's starting to happen in that resistor. And if we bring the current up even more, we should see that become more pronounced. So we can see now that we've still got 20 volts directly across the load, but there's 0.2 volts drop in the wiring, again simulated by the resistor. So the power supply is now outputting 20.2 to maintain that 20 volts there. So by sensing the voltage as close to the load as we can here, represented by this orange and brown wire, the power supply will adjust the output to maintain that voltage. I'll keep bringing the current up, and we'll see how high we can get here. That's getting up to about 900 milliamps, I believe. And so again, really close. We've still got the constant 20 volts across the load. We're now basically simulating almost 0.4 of a volt drop in the wiring, and the power supply is outputting 20.4 volts. And I'll see if I can get the current up really to the top end of what the power supply can give me, which is about 1.2 amps. And we're pretty close to 1.2 amps. And we can see again, constant nice 20 volts on the load. There's about, according to this, 0.53 volts drop in the system, and the power supply is outputting 20.6. So hopefully that's a good demonstration of what sense gives you on a power supply. Is it can sense the voltage at the load and adjust the output voltage accordingly to maintain the voltage at the load. And if you've noticed through this, I'm only tweaking the current flow. So this is a constant current load, and I've just taken the load current, basically to zero. The resistance here has gone as high as it can go in the test rig, and you can see we've settled down very close to 20 volts. One of the meters is making noise, and as I bring the current up, again you'll see the power supply on its own. I'm not touching the power supply, driving its output voltage up. We went into compliance. You can tell we went into compliance. The power supply clamped, so we'll bring it back out of compliance. Compliance is the maximum current the power supply can produce. There's a control on the front that we looked at earlier that limits the current draw. Once I get above about 1.2 something amps, the supply drops out. So there we're drawing about 1.2 amps. Still maintaining 20 volts at the load. It's driving an additional 0.57 volts into the circuit. This plus this equals 20.6, or really close to it. So anyhow, that demonstration went much quicker than I thought it would. As you can see, it's just kind of a, I'm using just cheap clip leads here. This isn't a perfect approximation. There's the potential that the 0.03 volts you see here, difference, 20 plus 0.57 is 20.57, not 20.6. There's actually a 4 hidden under there. May well be due to voltage drop in the actual leads here. There's most likely going to be some voltage drop across that wire, some voltage drop across that wire, and some voltage drop across the black wire here, and potentially, if my contacts aren't good, voltage drop there as well. So that 0.03 volts is most likely small voltage drops in the actual wiring. Again, within whatever the calibration of these meters are. So I think I've rambled on long enough. Let me stand up and take a look at the camera. Make sure everything's on screen. Hopefully that explanation made some sense. Anyhow, I'll get this edited up and posted, and we'll talk soon.